Okay, here's another application of Newton's second law for rotation. In this case, we have a pulley and a Samsung electric clothes dryer. It's connected to a Kevlar belt. It wraps around the pulley, as shown in the picture there. Pulley is essentially a solid cylinder, so we can look up its inertia in a table from the book, or maybe we remember it. The pulley has a mass of 1.2 kilograms and a 0.25 meter radius, and the belt has different tensions on either side. One side has 9.5 newtons of tension, the other side has 6.4 newtons of tension. And we want to calculate the angular acceleration of the pulley. Well, it's already got a free body diagram up here of what's going on. Interesting thing about ropes and pulleys is if the rope isn't glued to it, if it's just wrapped, it's going to always come off tangent. So this angle here is always going to be 90 degrees. Likewise, with this angle here that comes off of is always going to be 90 degrees. That's the only way they can act. Again, if we assume that they're very light, don't have a lot of mass, the pulley or the string. So Newton's second law says if we add up all the torques acting on that pulley, it will be equal to the inertia of the pulley times the angular acceleration of the pulley. And we've got two torques. Now in the counterclockwise direction, we got a torque from this one. So we've got a positive torque number 1, and then we have a negative torque number 2. And that negative, I look at the picture and I figure that out which way it's going to make it rotate. The convention is that counterclockwise is positive and clockwise is negative. And that'll equal I alpha. So what are these torques? Well, torque is, that's the radius 1, tension 1, the sine of the angle between radius 1 and tension 1. Subtract from that the radius for number 2, tension number 2, the sine of the angle for number 2. And that's going to equal our rotational inertia. And if we look up a solid disk or a solid cylinder, we'll find that its inertia is 1/2 its mass times its radius squared. And then that is multiplied by alpha. Well, these r's are all the same r, so that's just r. This tension is T1. This is sine of 90, so that becomes 1, right? I'm going to write that out as sine 90. And here it's the same r, tension 2, sine 90, and that's going to equal r/2 mr squared alpha. So the sine 90s become 1. Those just reduce to 1. And we could pull that r out of there because it's the same r. R T1 minus T2. That's going to equal 1/2 m r squared alpha. There's one r over here and over there. We can divide both sides by r. That r goes away. This one reduces just to that. And if we continue with our symbolic solution here, going to multiply both sides by t, divide by an m and an r, and we would get by 2 rather, not t. 2 T1 minus T2 over mr going to equal alpha. Now we can plug in all those numbers. So we'll get it down. And if I do that over here, we would get that it's going to be 2 times T1's 9.5 minus T2 6.4 all over the mass 1.2 times the radius, which is 0.25. And that's going to equal our alpha. Plug those into your calculator and crank it out. 2 times quantity 9.5. We get 20.66. Whoop, bump the camera. Sorry about that. So 20.66 radians per second squared is equal to alpha. There you go. That's how you do that problem.